first particle, first mass, where did it come from? How did energy get converted to mass? Within the nucleus, protons and we have neutrons, and these protons are positively charged.
Right.
And the basic theory that we know is like charges repel from one another.
Mm-hmm.
So in that case, nucleus should never have existed.
If you consider atom as a football field, proton is just a football, right? The nucleus are
Less than the size of
that just we are
no,
empty.
just a speck of dust.
Wow, we are empty. That means
Yes.
we are empty basically. We feel our presence, but it's nothing but force.
One of the tallest building in the world is the Empire State Building. So you take away all the void space away from the Empire State Building, and actual matter, if you take it together, it will be just a few millimeters. Television is the best example for your collider. The old television, not the
Where you get the
LCDs.
blur thing, is it?
Yeah,
I mean that.
the tube TV.
Okay, cathode ray tube.
Yeah, the CRT. CRT is the best example for an accelerator. You are accelerating electrons.
Wow. So this field particles do they have mass?
They, not all of them.
They can be massless field particles.
Yes.
Which means you can't see it, but you can only experience.
Yes. Consider an electron.
Mm-hmm.
Consider another electron. Both are similar, like negative charge.
Mm-hmm.
They're supposed to be repelled, and they will get repelled. Now that repulsion is happening because of an exchange of particles.
Wow.
Called photon.
And even if we touch our hands, we are not exactly in contact,
No.
right? It is just we are feeling the force of.
Yes, feeling the force.
It means when you knock off a quark from a proton.
No, you cannot knock off a quark from a proton.
Why not?
That is one speciality of quantum chromodynamics or strong nuclear force. A proton can never disintegrate.
Wow. Okay.
If you know the most fundamental particles and if you can understand the forces between them, it is possible for us to trace back. So it is that curiosity that led scientists to probe deeper into the atom, into the nucleus, and within the nucleus probe much deeper into the protons and neutrons.
Hey guys, welcome back to QED podcast. Today we are talking about a mind-boggling field in physics called quantum chromodynamics. As we all know, like anything which occupies space and has mass, which is called matter, we're all made up of atoms. Me, you, the water we drink, the air we breathe, everything is made up of atoms. So in our high school physics or our K-12 physics, we realized atoms are made up of, protons, electrons, neutrons. Protons and neutrons constitute a nucleus and their net positive charge. And this is held together by electromagnetic force, since electron is negatively charged. So our understanding about the fundamental concept in physics is stuck there. In this podcast, we are going to get into deeper level. When I say deeper level, we're talking about subatomic realm. What is inside proton? What is inside neutron? What is inside electron? So what is the most fundamental thing we can find? So the quantum chromodynamics deals with that. To have a conversation on this with me, I have Dr. Nilakanthan V K, and he's the assistant professor at St. Aloysius University, and he teaches particle physics. Professor Nilakanthan has done his advanced research or advanced studies in the field of quantum chromodynamics, hadron spectroscopy, and decay studies. And he's done his PhD on something called NN interaction. Welcome to the podcast.
Hello.
Yes.
Thank you.
So, and if you're watching this, if you know anyone who loves physics, please share the video and let's get it started.
Sure.
Okay. You have done you have spent at least 6-7 years of studies in quantum chromodynamics.
Yes.
Comfortably?
Yes.
Okay.
Okay.
And before I want to get into technical stuff, I want to get into philosophical thing.
Okay.
So since physics is nothing but study of nature,
Mhm.
like what is the reality, so that is
Okay.
actual physics. um, but studying quantum chromodynamics and
Mhm.
getting into subatomic level of studies and observations, what do you think we are made up of?
Uh, exactly. Actually, it is a curiosity.
Mhm.
Curiosity that we all have when we look around. Whatever when we look around, whatever we see, the leaves or even the wood or the tables that we have around us, what are they made up of? Finally, they're made up of atoms, and what lies within this atom? Within the nucleus, protons, and we have neutrons, and these protons are positively charged.
Right.
And the basic theory that we know is protons are positively charged and like charges repel from one another. So in that case, nucleus should never have existed.
Right. Right.
They will repel and they will just go in their own ways.
Scatter.
They'll get scattered. Why are they still held together? What force is holding them together? This is the strong nuclear force that we're talking about.
So you mean matter is nothing but force and
Yes.
like something with the weight.
Yes. This curiosity leads us in knowing more about the fundamental forces that exist in nature. What holds this entire universe?
Interesting.
So there are like few fundamental forces that
Mhm.
place everywhere.
So how do you define matter? Like how do you say what it is made up of? Like it's like
Matter is mainly few particles, few
With-
fundamental particles
with mass.
with mass, charge, and few other properties.
And held together by a force.
Yes, held together by a particular force. So it can be electromagnetic force or electrostatic force, etc. Or it can be a nuclear force, which is much, much stronger. Or it can be a weak nuclear force, which leads to decay of particles. I mean, the basic decay, radioactive decay, is due to weak nuclear forces. And there is this weakest of all the forces, that is the gravitational force.
Why do you think like physicists went deeper? Why didn't they stop at like atom is made up of just proton, neutron, electron? Why did what was the need to get deeper?
Again, curiosity not just to know what is there in nature. Where do we come from? It's not just about the humans, the anthropological part of it. It's about the entire universe. How did the universe evolve? What was the condition of the universe in its early stages? Or what was the energy scale? Or what were the forces that existed at the earliest stages of the universe?
Wow.
So we can have a flashback if we totally know the kind of forces that exist now. So if we know the most fundamental particles and if we can understand the forces between them, it is possible for us to trace back. So it is that curiosity that led scientists to probe deeper into the atom, into the nucleus, and within the nucleus probe much deeper into the protons and neutrons.
So you mean studying subatomic particles, like fundamental particles,
Yes.
would help us understand the evolution of universe, how it all things
Yes.
began.
Yes.
You
Exactly.
mean it did not just begin with the present understanding is universe began with just like beginning of the universe was just hydrogen atoms, but you're saying
No,
it's not the case. It began with the fundamental
most
particle,
fundamental particles.
then it
Most
became
fundamental.
proton, neutron, then
Yes.
became the hydrogen atom,
Yes.
then became helium, then multi-molecule. Like
Yes, and then
Wow.
fusion happened, stars, galaxies, etc.
so, what is proton is made up of?
So protons are basically made up of fundamental particles called quarks and gluons. Gluons are not. So there are two class of elementary particles. Any fundamental particle, for that matter, can be classified as fermions and bosons.
Okay, what is the difference?
It's based on the concept called spin, quantum spin. Spin is a property that any subatomic particle possesses. So these are fermions are particles which have half integral spin, like spin half, or spin can be spin
No,
3
before
by 2.
we talk about that,
Yes.
I think it's better to understand what are the fundamental properties
Yes.
of what
Yeah, they
properties
are
we
made up of-
see in the fundamental
Yes.
particles. One
Yeah.
is spin.
Yes.
Then
Obviously the energies.
energies.
Energy is usually not continuous. It can take only discrete values.
Okay, spin, energy,
Angular momentum,
momentum,
etc.
mass.
Mass.
Then
But mass and energy. So
it's interchangeable.
yes, because since we are working at a very high energy level, so the scale is usually we work at the relativistic scale.
Right.
So there we can consider mass and energy as the same
Right.
on the
So let's
on same footing actually.
mass and energy is interchangeable. So
Yes.
we'll consider energy and mass. One,
Yes.
spin,
Spin,
angular momentum,
angular momentum,
charge.
charge.
Is there anything else?
Yes,
Any
there
of the
are
factors that you guys deal with?
there are some other factors like isospin. Isospin is very much
Comes into
similar
spin
to,
only.
no, similar to
Okay.
spin, not
Okay.
exactly.
But these are the fundamental
Yes,
spin,
fundamental
angular
properties.
momentum.
These are
Okay.
fundamental properties
Properties.
that any fundamental
Okay.
particles.
So now
will
I
be
want to
having.
get into the properties deeper.
Yes.
Then we will go to the fundamental particles.
Yes.
So if we do that, we can understand and
So-
clearly visualize.
So when we consider spin, we usually assign a particular number to understand
Okay,
the spin.
help me visualize this. What is spin? Is it a rotation? Is it a movement?
No,
Or is
spin is not a movement. It is a number that we assign. For example, you consider energy of an atom or energy of an electron that is just revolving around an atom. It cannot take any value of energy. It will be in multiples of
orbital?
yes,
values,
orbital values.
Mhm.
So multiples of 1, 2, 3, etc. So that is called a quantum number.
Energy level.
Yes, each energy level will be quantized, and we assign a quantum number. So spin is just a quantum number like that.
Okay, spin is the quantum number of the fundamental
Yes.
particle.
Yes.
That is nothing but an energy level, you mean?
Yes. No. It decides how it should be located in a given energy level. The spin.
Okay, so it is -1 and +1, you mean?
-1 and +1 will be charge.
Okay.
Apart from this -1 +1, you have a -half and +half.
Okay, how is the spin is quantized? Like how is it measured?
With the help of magnetic field. So you pass a set of electrons, a beam of electrons. You apply magnetic field to it, they will get deflected. So according to classical electromagnetic theory, they should get deflected only in one direction. So what we observe is exact half of it, or almost half of it, will go in one direction. The rest will go in another direction. Why are they violating this classical electromagnetic laws? Because half of the electrons have a particular property, that is our spin. So the particles which go in one direction, if we assign them as +half, the rest of them will have the quantum number, spin quantum number, -half.
Okay, that is how you guys measure spin.
Yes.
Is it plus? I mean, like
Yes.
this kind of spin or that kind of
Yes.
spin. So how many kind of spins are possible?
This is for an electron. Two kinds of
No, not
spin.
electron, subatomic part. I mean this
More.
more. Okay.
More. There are more. Like there are particles that can have spin up to spin 2, or there are particles that can have spin 1.5, that is 3/2.
So it is the property of it deflecting.
Yes. No. Basically, the property, the different ways in which it can arrange in a given energy level.
Okay.
Basically, You have to think of certain probabilities or probabilistic ways in which we can arrange a particle in an energy level.
Okay, for me to understand, I will think it as the way how it behaves in that particular energy level.
Yes.
Is that a proper
Yes.
thing to keep in mind
Yes.
if you think of a
Yes.
spin?
Yes.
Okay, how it behaves in that particular energy level.
And given the various statistical probabilities of it.
What do you mean by statistical probabilities?
It can be like the way it behaves means it can behave in n number of ways, out of which we select only few.
Okay, so let's get into another property, charge.
Yes.
What do you mean by charge? Like, how do we visualize when we say positively charged, negatively charged? Inside, for molecules, we know it is the lack of electron
Yes.
and all. But when we speak about fundamental particles, like proton is positively charged, electron is negatively charged. Like, what is it?
Basically, positive charge, in the sense when people really started working on this electromagnetism, they were experimenting with current. And when they started detecting these particles, that is, they started discovering these particles. First fundamental particle that was discovered was electron. So what they did was they found a way in which they can accelerate electrons, get a beam of electrons, and they tried it on different plates. So in a battery, you usually have a positively charged plate and a negatively charged plate. So they tried to bombard these electrons to a positively charged plate and a negatively charged plate. So what they observed was, when they bombarded towards a negatively charged plate, they get accelerated, and when they bombard it on a positively charged plate, they get deflected or decelerated. So this is how you can make out if a group of particles you have is positively charged or negatively charged.
Charge is, you mean how it behaves in that
in a given
voltage
environment or in a given voltage.
So the proton having positive charge,
Yes,
neutron
having
neutral
electrically neutral.
Yeah,
It's not a
electrically
neutral
neutral.
charge. It is
But-
electrically neutral.
So
They don't
quantum
behave
chromodynamics
at all.
deals with how they got positive charge, how
Yes.
neutron is neutral,
Yes.
and how proton is positively charged.
Yes.
So you
And
dig deeper.
how they are held together within the nucleus,
Without
in
repelling.
spite of
Right.
in spite of the positive charge of the protons.
Okay, that is to do with the charge.
Yes.
Next is angular spin, angular momentum.
Yes.
So what is angular momentum of fundamental particles?
Anything that has a spherical, like, consider an atom, you can consider it as a sphere. So there is a spherical symmetry within that. That is, electron can exist everywhere within an imaginary sphere.
They follow the pattern inside the
Yes.
symmetry.
Yes. So wherever you have a spherical symmetry associated to that, we can have an angular momentum to that particular
As long
particle.
as there is movement.
Yes. And this movement will always on the sphere.
Okay, the protons don't move, right? They are stable. They vibrate probably, but if you talk about
within that range, who knows?
right,
They should be moving. They might be moving. Because nucleus has a size of 10 to the power of minus 15 meters.
10 to the power of minus 15 meters. Okay.
Yes. And protons are still smaller than this.
Right. One more thing is, in atom, if we consider atom as a football field, proton is just a football, right? The nucleus are
Less than the size of a football.
That means
Just
we are
no,
empty.
Just a speck of dust. If you consider football field as an atom, the speck of dust is your nucleus.
Wow. Not even football.
No. Imagine this. Okay, I'll give you in figures. The size of an atom is 10 to the power minus 10
That is Armstrong.
Armstrong.
Okay.
And size of nucleus is 10 to the power minus 15, which is called a Fermi.
Okay, Fermi, yeah. Right.
Femtometer or a Fermi. Now, take a ratio of both.
10 to the power minus 5. They net.
Yes, but take the other way around. 10 to the power minus 10 upon 10 to the power minus 15. So the difference is 10 to the power 5, which is 1 lakh meters.
Wow, we are empty. That means
Yes.
we are empty basically. We feel our presence, but it's nothing but force.
One of the tallest building in the world is the Empire State Building. So you take away all the void space away from the Empire State Building, and actual matter, if you take it together, it will be just a few millimeters size. So this is the amount of space each and every matter is occupying in this nature.
Even we are nothing but nothingness.
Nothingness,
Like-
vacuum.
Like even that's how these high energy particles can pass through us, because there is nothing to collide, because we are
Yes.
empty.
Yes, that came. That is where we can think of the historical development of particle physics.
Wow.
So it all began with Rutherford experimenting using alpha particles. You might have heard about alpha, beta, gamma decay
Right,
in
right.
radioactive decay. So as soon as alpha particles were discovered, alpha is basically, it is nothing but helium nucleus. Nucleus of helium is an alpha particle. So he was basically experimenting with them. He bombarded alpha particles, a beam of alpha particles on a thin foil of gold, because gold has very high atomic number. And what he observed was most of them passed through the foil. How can that occur? Only if there is empty space
Right.
within an atom. So first observation was most of the atom is empty space. Second observation was slight deflection at some places, and only at very few places backscattering. They just come back, which means that alpha particles are positively charged. So there is something a strong positive charge which is repelling these alpha particles, and they were called as nucleus. So that is where people understood that there is a nucleus within an atom. So this was somewhere in the beginning of 20th century, the beginning of 1900s. So this began with the entire field of nuclear physics. And slowly experiments conducted by various scientists. So neutron was discovered by Chadwick.
Right.
And then at the same time, theoretical development, quantum mechanics had begun by then. So quantum mechanics also was being used in various fields of atomic physics, and later slowly into nuclear physics. At that point, again, people were stuck because the energy with which they were playing was limited. They never used to have colliders or accelerators, particle accelerators. Those
You
days.
mean because we didn't have that much energy to operate a colliders?
Yes.
They had an idea of a collider, but we didn't have that much energy level.
Yes. The only colliders that they have was a television. Television is the best example for your collider. The old television, not the
Where
LCDs.
you get that blur thing, is it?
Yeah,
I mean
the tube TV.
Okay. Cathode ray tube.
Yeah, the CRT. CRT is the best example for an accelerator. You are accelerating electrons.
Wow. Yeah. Interesting.
So, a CRT or the cathode ray tube is the best example for an accelerator. So, that was the only energy scale we had probed into. But later, with the advent of high energy particle accelerators, people tried this experiment. It is called the deep inelastic scattering experiment. It was conducted at Stanford.
Which year?
1960s.
60s. Okay.
So we are from
Mhm.
early 1900s, we are in 1960s now. So there, what they did was they had a stationary proton. Somehow
Mhm.
they made a proton sit
Like levitate.
somewhere. Yes, and they bombarded very fast moving electrons on them.
Which is negatively charged.
Yes.
Mhm.
So proton are positive, electrons are negative.
Mhm.
What do you expect? Attraction.
Attraction.
A
Right.
very strong attraction if they are coming with a
That
very
force.
high speed.
Speeds.
Very high speed. But what they observed was most of the electrons passed without any deflection.
Most of the electron passed without any deflection.
Or
That means proton is also empty.
most of it.
Wow. Okay.
At some places and at 3 exact points, they found differences. At 2 points, what they found was there was strong attraction, and at one particular point, there was repulsion. So, how a proton which is positively charged is able to repel an electron which is negatively charged?
At some point.
Yes.
That means, okay, what I would conclude from the experiment is
At 2 points, so there are 3 smaller particles within the proton
wow,
which are positive, and one small particle which is negative.
negative, and rest of the part of the proton is empty.
Empty.
Wow.
And they call these small particles as quarks.
Okay, these 3 variations.
Yes. So at those 3 variations, or at those points, there is some particle which is affecting these electrons, and these particles were called quarks. And almost at the same period of time in 1960s, a theoretical development also had happened called the quark model. Independently using mathematical symmetries and various other considerations.
Pure theoretical
Yes. A scientist by name, physicist by name Murray Gell-Mann had proposed this quark model. And he had proposed that particles like protons are made up of 3 quarks with fractional charges.
Wow, just through calculation you figured out?
Yes.
Okay, do you know any specific details like what? I mean,
basically based on symmetry.
based on just studying symmetry.
Symmetry, there are different types of symmetries, discrete symmetries, continuous,
Right,
etc. Basically, symmetry.
But what I would understand is just with that concept of symmetry in mathematics, he was able to propose proton is made up of quarks.
Yes, quarks, and that too. For example, if electron the charge is -1, proton the charge is +1.
Right.
The quarks have fractional charges. So quarks are classified as, like, there are 6 different types of quarks, and each type we call it as a flavor, like flavors in ice creams.
Right.
So
6 types of quarks.
6 types of quarks. So each type is called a flavor, and each flavor has a name: up, down, strange, charm, bottom, top.
How they are different from each other?
Mass, charge, spin,
angular momentum.
Yes.
Okay, all these fundamental forces, I mean, nature of the fundamental particle
plays a role there.
Mm-hmm.
And even mass. The strange quark being the lightest, and the top quark being the heaviest.
Well,
so up quark. So after studying a lot, it was found that up quark has positive 2/3 is the charge, and down quark has negative 1/3
fractional charges.
Fractional charges. So a proton has 2 up quarks and 1 down quark.
So proton has a net charge of +1.
Yeah.
That
you add it up. 2 plus 2/3 You subtract a minus 1 by 3 from it, you will get a plus 1.
So proton will never have a fractional charge. It
No.
will always have a
Yes,
positive net charge,
1 net charge. And a neutron is considered to be made up of 2 down quarks and 1 up quark.
So charges cancel and keeps neutral.
It becomes 0.
So neutron has a charge, but it is net 0.
Yes. And at the same time, this was a period when a new theory, a new quantum mechanical theory was being born. It was the quantum field theory. So they had already quantized the energy levels within an atom. Like they knew that the energy levels within an atom is quantized in the sense they are not continuous.
Right.
They come in discrete pattern.
Okay. It means also measurable also, right?
Yes. So, and also properties like angular momentum, it can not have. Classically, that is, if you consider a rotating ball, it can have any value of angular momentum, any fractional value. But quantum mechanically, an electron within an atom can have only few values of angular momentum, only predetermined values.
That is also based on energy levels.
Yes.
Okay.
So when we come back to these particles, so they had already quantized the energy levels, angular momentum values, all these things. Now, what was remaining was radiation. So, according to quantum mechanics, even radiation comes in quanta or packets, which we call the photons. So, it was discovered and explained using a famous experiment called the photoelectric effect. It was discovered by Hertz, and the explanation was given by Albert Einstein himself. So, Albert Einstein said that radiation, light, comes in the form of packets. So, whenever we switch on a light, lots of particles are coming and hitting us. It is not just light waves. So, they are particles, and these particles are called photons. So, the theory of radiation also is quantized. Theory of atom, or whatever we have within an atom, everything was explained using quantum mechanics. But why not fields? Because we know that any force that exists between a particle is due to a field. For example, you have a positive charge and a negative charge. They get attracted because of an electric field or an electromagnetic field. You keep two masses nearby, they get attracted.
Gravitation.
Yes, gravitation. There is a gravitational field that is acting between the two particles or around any particle. You keep a particle in space, there is a gravitational field around that. Or you keep a charge in space, there is an electric field around that, or an electromagnetic field. If a charge is moving, there is an electromagnetic field around that. So scientists started to realize that even these fields should be having a quantum nature.
Discrete.
Yes. The concept of discreteness, not continuity. So that is where quantum field theory came into picture, and scientists devised a mathematical theory which states that any interaction takes place by exchange of field particles.
Wow. What is field particles?
Gluon.
Okay.
So that is the gluon which is being exchanged between the quarks.
Okay. So each quark is held together by a gluon. That is, gluon is nothing but
a force carrier.
Particle.
A force carrier.
Force carrier.
Which is nothing but the field particle.
Between these particles.
Yes.
So these field particles do they have mass?
They, not all of them.
They can be massless field particles.
Yes.
Which means you can't see it, but you can only experience.
Yes. No, even Yes.
I mean, that's what I mean.
Experience
if I was a
it
quark,
using. Yes.
I mean, if we were two quarks,
It will experience a force,
Mhm.
but that force is due to a gluon.
okay, gluon is a force particle.
Yes.
Okay, got it. It's a quantum field theory. According to
Yes.
quantum field theory, you mean?
Gluon is a particle that is being exchanged between two quarks.
Okay.
So quarks feel the attractive force between each other because of the exchange of this gluon.
Got it.
Now, forget about this quarks. Consider an electron.
Mm-hmm.
Consider another electron. Both are similar, like negative charge.
Mm-hmm.
They're supposed to be repelled. And they will get repelled. Now, that repulsion is happening because of an exchange of particle
Wow.
called photon.
Hmm.
The same photon which comes out when you switch on a light.
So photon is not
It's-
charged, right?
No,
It's a neutral
it's
force.
a neutral particle.
Mhm.
Gluon is also a neutral particle.
So when you mean electrons will get repelled with each other,
Yes.
that means they exchange photons,
Yes,
and that's how they repel.
yes.
Okay,
And
that means
the exchange of photon are responsible for the force that they are feeling.
photon is an energy, light energy.
Yes.
Quant packet of light energy.
Not just light energy, it can be any. For example, any radiation behaves as a photon. So X-rays
Mhm.
X-ray photons are much more energetic
Right. Then
compared to the light
visible light.
visible light energy.
So okay, so you mean why they get repelled? Because they get the momentum from the photon.
From the force carrier.
Ah, right. That answers my fundamental question. Why do they repel?
Yes.
Like we can visually visualize repulsion, but we can't figure out why repulsion. Now I understand it is the collision of
Yes.
the photon.
With the gluon.
Oh, okay. Now
In
I
a
can-
way.
Right.
In a way. But again, the question, if you have a positively charged particle and a negatively charged particle, why do they attract? So it's not exactly a collision. It is emission and absorption. That is, electron here emits a photon and the same photon is absorbed by the electron here.
Wow.
So in that process, there will be
Mhm,
repulsion
mhm.
or attraction based on the charge.
All right. And even if we touch our hands,
Mhm.
we are not exactly in contact,
No.
right? It is just we are feeling the force of
Yes, feeling the force.
maybe at subatomic it is quantum force. Is
Yes.
it? I mean, I'm just thinking. It's quantum force.
Yes.
Oh, nice. Okay. Then what happened after quantum field theory?
Yes, so quantum field theory. So with quantum field theory, they could explain exactly how electrons, protons, etc. behaved, and that theory was termed quantum electrodynamics.
What is quantum?
The
Okay.
classical
Mhm.
electromagnetic theory or electrodynamics explained with the help of quantum mechanics. Well, and relativity, because we use relativistic
Right.
velocities or the speed or the energy scales at which the charges or the particles are considered are relativistic, ultra high velocities.
Mhm. Interesting. That is quantum electrodynamics.
Yes.
Okay.
It can be considered as a marriage of quantum mechanics and relativity.
Mhm.
This quantum field.
The fields merged and the maths equated very well.
Yes.
Okay, that gave us.
So for
a new reality
electrodynamics,
of
the theory is for electromagnetic theory, the theory is quantum electrodynamics. For strong forces, the strong nuclear forces, the theory is quantum chromodynamics.
Okay, could you repeat that? Quantum electrodynamics.
For electromagnetic theory,
Mhm.
the quantum field theoretical version
Mhm.
is called quantum electrodynamics. For electromagnetic forces. For strong nuclear forces, the quantum field theory version of it is quantum chromodynamics.
Okay. Now I want to also get into deeper into this one. Weak, strong nuclear force
No.
and.
Before that, again,
Mhm.
one property that has to be mentioned about quarks
Mhm.
is color.
What is color? I mean, they
Yes.
actually have a color.
No,
Mhm.
it's not that they actually have a color. No, you cannot even see them.
Right.
So color is another property like charge, which is almost similar to charge.
Okay. It's not charge.
It is
similar.
not charge. So charge, you have two types of charge, positive
Right,
and
right,
negative.
right. So
In a
color
similar
is
manner,
a
we can think.
fractional charge or something?
No.
Okay.
Color is just a different property. There are three types of color.
Mhm.
So based on this color, also this force works, depending upon the dynamics of the color.
Mhm.
And any compound particle, like a proton, is colorless. So the combination of red, blue, and green will give you white.
Colorless.
Colorless.
That's why they named color.
Yes. It is a property. When added up, will give you a compound property which is colorless. Yet another property for quarks. Only for quarks and gluons. Not for other
fundamental particles.
Yes. Not for other fundamental particles like electrons.
So why not?
Because they exist at a smaller scale and a much more a higher energy scale, where the energy scale that exists in that particular realm defines with degree of freedom. You might have heard of degrees of freedom. Degrees of freedom are different ways in which you can possess energy. For example, a free particle kept in space can have 3 degrees of freedom, macroscopically. I'm not talking microscopically.
Right.
A macroscopic particle, for example, if you keep a ball in space, it can have 3 degrees of freedom. 3 degrees of freedom means it can move in 3 different ways. It can either shift its position from one place to another. That's
That
called
means
translation.
we are talking about 3-dimensional world.
Yes.
What if? Okay.
So it can move in 3 different ways. One is actual motion, one is rotation, or one is vibration.
Oh, could you repeat that again?
Any macroscopic particle can have 3 different degrees of freedom. Degrees of freedom is different ways.
Right, it can move.
It can move.
Okay.
Or it can acquire energy.
Right.
So when it moves, it acquires energy.
Right.
So different ways in which it can acquire energy. When you go to such a... So we are not talking about subatomic world here. This is subnuclear.
Right.
So at this range, the energy scale is also so high that the number of degrees of freedom is more. So color is the additional degree of freedom that we are giving, with which everything fits perfectly. And testing this, all these things have already been tested at various collider experiments, accelerators.
So you mean there are 6 quarks?
6 type of quarks. Each quarks come in 3 different colors. So 3 times 6 is, so we have 18.
They have their own color, they have their own fractional charge, and they have their own angular momentum.
Yes.
Okay. And is there any different gluons in a sense between this? I mean, there are, just like there are 6 different type of quarks. Like, is the gluon the particle
based on the
force,
properties, based on the properties, or based on the properties that we that is we understand from mathematical symmetries, there are 8 different types of gluons.
So that is based on the possibility of 2 quarks interaction.
Yes.
So that gives to 8 different type of gluons.
There are now there are 6 type of quarks. Each quark comes in 3 colors. So total there are 18 quarks now. And in nature, if there is a particle, you have an antiparticle of that. That is, for an electron, there is an anti-electron, which we call the positron. So for a quark, there is an anti-quark. So 18 quarks and 18 anti-quarks. So the number is 36 now. So based on the different types of interactions that can occur between these type of quarks and anti-quarks, the number zeroes in to 8 types of gluons. I hope you
Got it. Somewhat. Yeah, now when you mentioned the antimatter,
yes.
like anti-quark or positron, anti-electron.
Hmm.
So what are these? Like, help me visualize the antimatter part of it. Like, how is possible? I mean, what is the math or like, what is the math or logic behind the existence of antimatter?
Yes. The basic idea, okay, you can visualize it from the concept of basic electronic devices. Shall we?
Yes.
Yeah. Now, let us think. So, in electronic devices, these devices basically work based on flow of electrons.
Right.
Now, an electron can flow in a device only if it is coming out of an atom.
Right.
Because they are free electrons. They are
Right.
free to move. If they are within the atom, they are bound within that atom.
Bound by electromagnetic force.
Yes. So, in electronic devices, the electrons that are moving are free to move. Now, what will happen when an electron comes out of an atom? There is a vacancy of an electron created there. So, vacancy of an electron which is negatively charged should be positively charged. I hope you understand.
Got it. But it is not okay. Positron, does positron has
No.
mass?
Yes, exactly same mass as that of an electron,
Mhm.
but opposite charge. Every properties will be same except for the charge and spin.
How was the mass got replaced? Like in a
No.
sense.
In the electronic devices, you don't have a
No.
positron.
Not on the electronic, but when we talk about atomic,
Yes.
if you knock out an electron,
Hmm.
so you said there is a creation of
A vacancy.
positron.
No.
Okay.
Positron is not created. there.
Okay.
In
Vacancy.
an electronic device that is
Mhm.
in an atom, for example, you knock out an electron,
Mhm.
there is a vacancy that is created.
Right.
We call that a hole.
Yes.
It's known as a positive hole. So, entire working of any electronic device, a transistor,
Right,
an
right.
IC,
Mhm.
or all
Solar
whatever
cells.
whatever is made up, like our computers or cell phones are made up of these ICs
Mhm.
and chips. All these are working based on electronics, and this is working based on flow of electrons and simultaneously flow of holes. So if electrons are moving in this direction,
Mhm.
corresponding holes are moving in the opposite direction.
Okay. Now
That is
atom is there.
yes.
You knock off an electron.
Yes.
A hole is there. Vacancy is
A
created.
positive vacancy is created.
Okay. How do they flow? Like they're supposed to be where the atom is, right?
Yes. But when a free electron is flowing,
Mm-hmm.
correspondingly, there will be one electron will try to come and sit in that particular hole.
The
In
adjacent
that
okay.
vacancy
Right.
from the adjacent atom.
Mm-hmm.
So the hole shifts.
Now I got it. Now, okay. But where is the positron picture here? Like,
Yeah, no, this is in a bound system.
right.
Within a device.
Right.
You are talking about a solid.
Right.
When this happens in a vacuum,
Oh, right. Where there's no matter nearby.
when there is lot of energy,
Mhm.
that energy can naturally create a pair of electron and a positron.
This is where energy is converted into matter.
Yes.
This
It's
is
called
like-
pair production.
Uh-huh.
And the opposite also can occur. A pair of electron and positron can combine to create
release energy.
enormous amount of
annihilation
energy.
and
It's called annihilation and pair production.
okay.
Pair annihilation and pair
Mhm.
production.
That's what happened in the beginning of the universe. Like there could have been a huge energy
Yes.
condensed to matter
Yes.
or matter.
So it's not just electron positron pair creating energy. or energy being created, energy creating electron and positron pairs, energy created quark and anti-quark pairs,
Wow, okay.
and the associated gluons.
Nice.
Energy created positron electron pair and the associated photons.
So tell me about anti-quark.
Anti-quark is the antimatter of a
Quark.
So if the quark has plus 2 by 3 as its charge, its anti-quark will have minus 2 by 3, and exactly opposite of all the properties. If its spin is positive, the spin of the anti-quark should be negative.
That means when you knock off a quark from a proton.
No, you cannot knock off a quark from a proton.
Why not?
That is one speciality of quantum chromodynamics or strong nuclear force. A proton can never disintegrate.
Wow, okay.
You try to bring these quarks apart again, like
through an energy,
with using some kind of force. Naturally, it will find a way to bind with some other quark. More and more new particles will get created.
Oh, that's where exact energy is translated into mass.
Yes.
Like if you put energy, like you need energy to knock out a quark from a proton.
Yes.
When you put an energy into the
proton, to separate an electron from an atom, it is very easy.
Yes, photoelectric effect.
Yes.
But here in terms of quark, the proton,
you cannot do that.
Like no, help
once
me visualize
you do
this.
that,
okay.
Once you try to do that,
new mass is created.
Yes.
That is where energy is converted into mass.
Yes.
Am I right? I mean, am I thinking right?
Yes.
Okay.
I'll give you the best example. Imagine you have 3 quarks in a proton.
Okay.
One of the quarks you are trying to pull it off. So there is lots of energy involved there. And that energy will create a quark and anti-quark pair. Understood? And the new quark that is produced is put into that proton. And the anti-quark that is produced will go with the quark that you have pulled out.
Oh.
It forms a quark and anti-quark pair.
And energy is released.
Yes. So the proton is back there without any change. And the new quark anti-quark pair is a different class of particle that is called meson.
Can you repeat that again?
Quark and anti-quark pair
is
a different class of particle. That is, proton is made up of 3 quarks.
Got it. Okay, meson is formed when quark and anti-quark is combined.
Yes, combined. It forms a bound system like proton.
Is it a fundamental particle as well?
Yes.
Mesons.
Yes.
Mesons are made up of anti-quark and quark.
Yes, a part of hadron spectroscopy that our team has done, our research team has done, is mainly studying the mass and decay properties of various mesons.
Mesons have mass?
Yes. They are made up of quarks.
And where do they? Do we? If we speak about atomic scale, atomic realm.
Where do you find these mesons?
Mesons, right?
Okay. Mesons are usually found in nature. They are found in atmosphere. You must have heard about cosmic rays.
Right.
Cosmic rays are very high energy particles that comes from outside the atmosphere. That is from the outer space.
From the solar system.
The entire, need not be solar system. Might be from
the galaxy.
Some other galaxy that is
light years
away.
Right.
Due to some explosion that has happened, lots of particles, a rain of particles, or a swarm of particles have entered Earth.
Bombarding us.
Yes. So these particles, when they encounter our atmosphere, there are lots of particles to collide with. Molecules, dust, air, not just that, other electrons, protons, and other stuff. So when they collide, what happens is they disintegrate into smaller particles, which we call decays.
Oh, nice.
So one of the decay mode is they get decayed into mesons.
So
you try to separate a quark. When you separate it enough,
you get the
energy is sufficient to produce a quark anti-quark pair,
which leads to meson.
meson and
is the
another
that will be
another
stable
proton,
there,
yes.
right? And is meson stable? Like, I mean, what is the lifespan of meson?
very less. They decay
Again.
soon into electrons.
Oh,
That is what we
interesting.
call as weak interaction. Another fundamental force. Not just electron, there are other types of other particles which are very similar to electrons. So, okay, now let us go back.
Mm-hmm.
Fundamental particles can be classified into two types: hadrons and leptons.
Okay.
Hadrons in Greek means heavy. Leptons in Greek means light. Hadrons are again made up of baryons and mesons. Baryons are nothing but proton, neutron, etc., which are generally made up of 3 quarks.
Mm-hmm.
Mesons are made up of quark anti-quark pairs.
Right. Just one quark, but they're complementary with other antimatter.
No. Quark and anti-quark pair are bound together to form a meson.
Right. But just one quark, one type of quark.
No, need not be.
No.
Need
I
not
mean,
be.
they don't have two different quarks. They just have quark and anti-quark of the same.
Not same type. Need not be. That's what I was saying.
Oh my God. Okay. It's too much
So
variation.
imagine the number of possibilities that you have. So
Right.
each possibility is a type of meson.
So hadrons are hadrons are classified again to can be meson or it can be
Baryon.
baryon. What
Ba-
about
Lepton.
leptons?
Leptons are fundamental. Electron.
You can't,
No, you can as of now.
as the present knowledge of physics, you can't. You can't
It's
get
not
into
knowledge of physics. It's present at the present energy scale.
energy scale.
We have not
Okay.
divided it yet.
What do you mean by energy scale?
We have not probed into the electron.
So,
We have probed
in
into
order
the-
to get inside the electron, we need a huge energy.
more energy.
Okay, tell me about the energy scale. Where are we in the present, and how
All
much of energy scale is required to probe inside the electron?
Should we go in the ascending order or the descending order?
Any
That's
order
my
is
question.
fine. Just blows
For
my mind,
example,
anyways.
the amount of energy that comes out when we switch on a light is electron volts. Few electron volts.
Right.
And the amount of energy that we observe when very high energy electrons are bombarding relativistic scale, it is few hundreds of kilo electron volts. Within the nucleus, when we consider, the range of energy is million electron volts, and within the protons the energy range is giga electron volts, and interaction between the quarks is few hundred giga electron volts or more than that. So the highest energy scale that we have reached in collider or accelerator experiments are around few tera electron volts, that is 10 raised to 12 electron volts.
Large Hadron Collider. They operate in teravolts.
Tera electron volts.
So to get into this quark
Yes.
or electron,
Yes, you need an energy scale which is much greater than tera electron.
like double it or
Double will not be enough. You should increase order of magnitude by 10
100.
to the power, not just 100, maybe thousands,
that would be 10 to the power 14, 15.
or 10 to the power 18.
What is 10 to the power 15 called? Quadrillion.
What?
Leptons are electrons.
Leptons. Yes.
Leptons are electrons.
Electrons, not just electrons. There are other particles like muons, tau particles, etc.
So you mean electrons have cousins,
Yes.
like variations, like
Variation. The thing is that muons, tau particles are heavier than electrons, but the property is the same.
right. They also
They are
negatively
produced when
charged.
these mesons or baryons decay.
Okay, now let's we can go in a different direction, two
Yes.
direction. We can go the hadron direction. We can go to the
Baryon,
no,
lepton direction.
lepton direction.
Yes.
So, which
You go to
is
the lepton direction, we deal with weak interactions, weak nuclear force.
okay. Let's go with the lepton interaction.
Yes.
Then we can go into hadron.
Best example for a weak nuclear force is the beta decay. Might have heard of the beta decay when you have studied basic radioactive decays in your elementary school.
Right. That's what Marie Curie observed.
Yes, exactly. So radioactive beta decay is the best example for a weak interaction where an electron comes out of a nucleus. Now, according to our understanding, electron is something which exists outside the nucleus. How is it coming from within a nucleus?
Right. Wow, interesting.
What happens there is a proton or a neutron gets converted into one another. So in beta decay, a neutron gets converted into a proton, giving out an electron and another lepton called a neutrino. A neutrino is basically a chargeless and almost massless particle.
Which is energy, is it? I mean, they
Which
have
has
energy, right?
but
Massless energy.
almost massless.
Oh, it is the hybrid between mass and energy. you can
Yes.
say. Wow. Okay. Neutrino.
Yes.
I have seen the pictures of neutrino observatories, like so many
Yes.
gold
Yes. Yes.
things.
Yes.
Like, and
It is
India was
called
leading
Super
in that.
Kamiokande Observatory, which
Right.
exists in Japan.
Right.
Yes.
Okay. Now beta decay, weak nuclear interaction, where you see
Where hadrons get converted from one form of hadron to another form of hadron,
giving out lepton.
giving out leptons.
Okay.
So it can be electrons, can be muons,
Mhm.
or it can be tau particles.
That means you can create electron out of proton.
Yes. Yes, not a proton, that is highly difficult,
But from
but
neutron.
out of a neutron.
Oh, out of a neutron you can create an electron
Yes.
and convert. I mean, leaving that neutron into
It's
a proton.
not creating. Every neutron gets converted to a proton every 15 minutes.
Wow. Okay.
Not like imagine you have n number of neutrons in a given sample. Half of it will get converted to protons every 15 minutes.
Then how do they keep the net charge? That means even proton should be converted into neutron to keep a stable.
Number is so high. That is why the entire that is how we have entire concept of radioactivity. So all these things happen within a radioactive particle, not a stable.
Okay.
Sorry.
That's what I mean. Okay.
Not a stable particle.
Got it. So going back to the leptons, so you mentioned other variations like tau particle and
Yes.
what are the other cousins of electrons?
Muon.
Muon. Okay.
Electron being the lightest, muon being the intermediate particle, and tau particle being the heaviest.
Can tau be encircling the atom or encircling a nucleus?
Hypothetically, yes. Practically, no, because tau particles are very unstable.
They again disintegrate
into smaller cousins.
Like electrons.
Yes.
Fundamentally, all of the leptons converted to
heavy particles are very unstable for that matter.
So you mean electron is the lightest particle in the lepton category?
Yes.
So in lepton there is nothing lighter than electron.
No.
That's why electron is
and the neutrino associated to the electron. So there is a new type of neutrino.
But neutron is without mass. Electron has a mass.
Neutrino, not neutron.
Yeah, neutrino, right?
Yes.
Neutrino doesn't have mass.
Almost zero mass. Not a.
I mean, electron has 10 to the power minus 31 kgs, right?
Yes.
But neutrino, if you speak in that scale, what would that be like?
Neutrino.
Like not at all measured.
No.
That
very hard to measure the mass of a neutrino.
One who measures the neutrino's mass will definitely win the Nobel Prize.
Yes.
Wow.
Almost zero.
I mean,
mass.
I think
zero mass.
Okay.
Massless. for all purposes. Uh,
Does that happen like in our like the stable environment where you
we are
see
giving out.
neutrinos?
We are giving out
We are giving out
swarms of
neutrinos
electrons every minute, every 15 minutes. Now think of it as see, your blood consists of potassium. Potassium has an isotope called K40 isotope, potassium 40, which is radioactive, which gives out beta particles. Beta particles in the sense which gives out electrons.
Right.
So along with electrons, you are giving out neutrinos as well.
Right. What about the stable atoms?
So if you take a collection of potassium atoms in your body, only few of them are the radioactive. The others are stable.
Right.
Now take a tree for example.
Right.
How do you calculate the age of the tree?
Right.
Using radiocarbon dating. That is because you have C14 isotopes in your
Right. That's how you can measure the half-life and calculate
the age.
But I'm talking about what do you see how if you consider a stable atom like a stable isotope.
Yes.
Stable isotope is the right word. And what is the scenario when it comes to generation of mesons, neutrinos? Are they very apparent, like are very frequent?
The probability is very, very less in this, whereas it is frequent, very much frequent in these radioactive.
Okay. So what in radioactive is they're coming back to the stable state of energy.
Yes.
Okay.
They give out this thing, and then they become.
So when we talk about fundamental particle, electron is the most stable energy level.
Yes. So that's why we say quarks and leptons are the most fundamental.
Okay.
Among the particles.
Interesting. So wow. So let's get into hadrons.
Yes.
Okay. So hadrons has two types of variations. It can be baryons
and mesons.
Mesons. Okay. Baryons are nothing but the protons,
neutrons, etc.
Right.
There are other exotic varieties of baryons which are made up of heavier quarks, but the problem is again the stability. So in nature, in the cosmic rays, as soon as a very heavy baryon is created, gets disintegrated into other lighter baryons and leptons. So these things happen. The time scale needed for this is less than a femtosecond. Femtosecond is 10 raised to minus 15 seconds.
Wow. How did they even observe, or this is just a theoretical calculations?
Theoretical calculations and observations are there. Observations now they do it using accelerators. From cosmic rays, what they did was they actually had chambers with some vapor in it. What they do is at the end of that chamber, they have a photographic plate which records the path followed by each elementary particle. So they give a signature path for each type of particle. For example, electron always traces one particular path. All the electrons. All the protons traces some other type of path. So each path is a signature of that particular particle. So in earlier days, this was it's called the cloud chamber experiment. And the most famous type of cloud chamber is the Wilson's cloud chamber. So that is a way the particles used to be detected earlier. So after a point, suddenly one particle gets split up into two particles and it goes into different paths. What is that? It is a particle decaying into two smaller particles.
Right.
So that was how they detected a decay in the earlier days. Now, totally using the help of accelerators. Colliders also, they have detectors which can map the motion and they can understand.
Okay, so my next important question is, as you said, it is very strange that a nucleus is net positive charge and yet they are intact.
Yes.
How, what keeps them together? Like, what keeps the proton and neutrons bounded inside the nucleus?
Yes. It is basically this strong force itself,
Strong nuclear force.
or strong force
Mhm.
itself. That is, a very strong force exists within the protons and within the neutrons between the quarks.
Yes, inside the proton.
Yes.
Right.
Now, there are theories which suggest that
Mhm.
these quarks take a part in interacting
Oh.
outside their domain. That is, if there is a proton and neutron lying very near to each other,
Mhm.
the quarks within the proton interacts with the quarks within the
Mhm.
neutrons.
Do you
nearby.
mean exchange of quark
exchange
or
of
the
gluons?
interaction?
Exchange of gluons between quarks in the proton
Oh.
and quarks in the neutron.
But there's no exchange, just the gluon.
Gluon is exchanged.
Gluon
The
is
particle
just
is not exchanged.
gluon is just a
Mediating particle.
force particle,
Yes, force carrier,
force carrier.
or what we call as a mediating particle
Right.
in quantum field theory.
Right. So again, gluons don't have mass, right? Just-
Don't have mass.
Right. That is what strong nuclear force is.
Yes,
That is exchange of gluons
gluons.
in terms of what keeps the nucleons in the nucleus of an atom strong. I mean,
Yes. So there are two theories. One is this,
Mhm.
or yet another theory which was given very long ago, but it is yet a competing theory. It is
Mhm.
called a pion exchange. Pion.
Okay.
Pion is a type of meson, pi meson.
Okay.
Pi meson is being exchanged between these nucleons. Nucleons in the sense
Mhm.
protons and neutrons, or neutrons and neutrons, protons, etc.
Right.
The same way in which gluons are exchanged between quarks. Pions,
Pions is nothing but a quark pair.
quark antiquark pair.
Right.
So a quark antiquark pair suddenly gets exchanged.
To another nucleon.
Yes, gets absorbed.
Mhm.
So it is like the energy
Mhm.
creates a quark antiquark pair
Right.
from the neutron end
Mhm.
that propagates and reaches the proton end, and that energy is absorbed, or that particle is absorbed in the form of energy by the proton.
Mhm.
And this emission and absorption part keeps these particles together.
Wow. Wow.
That is one theory. Another theory is nucleon interaction due to exchange of gluons between the
Mhm.
quarks. That is, a proton is having quarks.
Right.
A neutron also has quarks.
Right.
So the quarks between the quarks situated in each particle is
Mhm.
exchanging a gluon.
So that was your PhD as well, right?
Yes.
N interaction.
NN interaction, or a nucleon interaction using QCD based models.
So what did you do there, like exactly?
So we had taken one particular potential
Mhm.
which gives certain amount of, that is, which gives stress amount upon gluon exchange between two nucleons,
Mhm.
and we calculated the energy released, or energy that is being exchanged
Mhm.
during such an interaction,
Mhm.
which gives you the force also.
Right. Right.
And we we got a set of data which we had a plot which we plotted, and which matched, and the plot was similar to the experimental plot of neutron
Mhm.
proton collision, or a neutron collision.
Nice. So you mean you came up with a theoretical calculation between the gluon exchange inside a nucleus,
Yes.
and then you compared that calculation to the data which was available in the experimental
Yes.
physics during colliders, and then
Colliders.
it matched,
Yes.
and then you proved something.
we published it.
What was your publication? Like, what did you exactly prove?
Role of gluons in nucleon interactions.
Oh, okay. You worked on the cutting edge theory then.
Yes, but this was there even before. This theory was there even before, but the particular type of potential was given by our a new potential, for example,
Like
new form of mathematical term,
Wow,
mathematical potential.
Mhm.
Potential means a potential defines a particular type of force. For example, electrostatic potential defines electrostatic force. So here, the type of potential that we have, not just me, the
potential.
team
You mean
entire-
the difference, right?
Yes.
Right. Low and high and
Yeah, potential
levels.
difference will give rise to a potential energy.
Right.
So because of the potential energy, there will be a potential in that given region, which will give rise to that force. For example, imagine you are keeping some object at this height, at a height. So the difference in height will result in a potential difference, and because of which there is a gravitational force there. Force between the earth and the object that is kept at a height,
Right.
and that we call as a potential.
So
And we can write the exact form of a potential using a mathematical equation.
So you introduced the concept of potential
Yes.
in terms of
Not actually me, a team.
okay.
So the team comprised of my supervisor,
Mhm.
even his prior team,
Right. Right.
and
So
our
you were
team.
part of that knowledge.
Yeah, a part of
we-
a team
Mhm.
which introduced a particular potential, which helped in calculating the amount of force that existed between nucleons.
And how do you measure that force in terms of subatomic level? Like force in the physical terms we express in terms of Newton, right? Newton.
Yes.
So how do you
Here
express
we
the
convert
force?
it into energy,
For-
into the
how-
amount of potential energy that is there.
What is the relationship between force and energy? What is the formula between force and energy?
Work done is force times the displacement, and that is measured in joules.
Right.
Work done. The work done potential is the amount of work done for that particular configuration.
Okay. Oh, that's where potential come here.
Yes.
Okay. And how did you guys like calculate the force and energy in the subatomic level here?
We calculated, we took the, basically what we did was we found the energy by solving, like in quantum mechanics, we solve certain equations called Schrodinger equation or Dirac's equation, etc. So once you solve these equations, you will get set of energy values
Of that particle
of that
particle
system.
interaction.
Yeah, of the system.
Mhm.
So that is what we could understand as the force existing
Right,
between.
right. So then you guys, you guys measured the force
Mhm.
theoretically using
Yes.
calculation, and then what was the experiment? How did you prove in?
No, we did not do that.
Okay, you compared the experimental data.
Yes.
But how do they generally
They
understand?
collide.
Okay.
They collide particles.
Mhm.
So when they collide particles get scattered in all possible directions.
Right.
So they get a cross-sectional area of scattering. So the amount of area, for example, if the area is more, then the interaction also was more. You can think in terms of an accident. If particles have scattered to a larger extent during an accident, it means that the impact of collision was more. So if the cross section of scattering is more, then the force is much more, and force is less if the cross section is less. So experimentally they measure this cross section or the area into which scattered particles move into.
Right.
So that will give, so you can convert that amount of area into the energy of scattering or the force of scattering. So that they plotted as a graph. So we compared their plot with ours, which matched.
Right. So from where
Which
did you
was-
take the experimental data? Like, is it from the Hadron Collider, or which colliders are
No,
you to?
all these colliders, what they usually do is they submit their data into some open source.
Mhm.
That is, we usually call it as the particle data group.
Particle data group.
Yes,
Right.
it is updated once in 2 years,
Mhm.
and it is published as a book.
So
It
they
is an
release
online
all
book
the data
available.
inside that
All the
database.
particles, all the data of all the particles that have been discovered till now.
Mhm.
So it is almost more than 1,000 pages.
Mhm.
So it is a PDF copy that is readily
Like,
available.
do they upload the raw data, the what you see in the collider, or they understand it and they
Yes,
refine
they
the
understand
data?
it. They
Okay.
understand it, refine it, classify it, and in form of tables
Mhm.
represent it. For example, particle, neutron. Every year, more and more properties of neutrons are discovered.
Wow.
So 2 years from now,
Mhm.
maybe the number of pages in the book that is being published will increase because more and more data about the same particle
Mm.
will be published.
So
So all
calculations get
these,
accurate,
all the colliders in the entire world contribute towards this particle.
including China.
China, including India.
Okay.
In India, we have lots of.
How many
particle
colliders
accelerators.
India has?
Yes, India has in high energy colliders we have one in TIFR, Tata Institute of
Mhm.
Fundamental Research, Mumbai, which works in nuclear range, nuclear that is low and medium energy nuclear range up to million electron
Mhm.
volts. And then there is Inter University Accelerator Center in IUAC in New Delhi, and then there is uh, one VECC,
Mhm.
Variable Energy Cyclotron Center in Kolkata. Uh, According to my knowledge, I think that is the highest energy accelerator that we have in India.
Oh, it's below nuclear range.
Yes,
It's subatomic
yes,
range.
subatomic. It goes into subatomic range,
Interesting.
into hadrons, etc.
Mm-hmm. So you keep yourself updated with this database.
Yes, we have to. We have
Okay.
to.
So
Yeah.
when is the last time you checked the database for your calculations?
Very recently, for that is because whenever we are doing some data, we need certain parameters in calculating. For
Right.
example, whenever we solve some equations, solve some differential equations, we need parameters like mass of these quarks. So updated mass of these quarks from the experimental data,
Mhm.
we will have to refer it again and again.
Amazing.
So few years ago,
Mhm.
when we were working on a particular quark mass, now it might have changed only in a decimal level, but
Right.
still that makes a
Oh,
considerable amount of
the
change.
accuracy
Yes.
keeps getting better and better.
Yes, it
Not
keeps
just mass, but also the charge level, but also the
spin,
angular movement.
angular momentum,
Wow,
everything,
okay.
magnetic moment.
Mhm. But how do you? Okay, you said even proton, when you look
Mhm.
inside, is really empty. Just like atom, how atom is empty inside, just
Yes.
like that, proton is also empty.
Yes.
I was thinking like quarks and quarks interact like in the physical touch,
Mhm.
but how do you, like, if you had
They are
to
far
tell
away.
me to visualize,
Mhm.
like if you help me visualize, what is the, how these quarks,
Mhm.
we know like quarks interact with gluons inside a proton.
Yes.
I mean, proton is a huge, or like if you say, again, we will take the football field reference to a
Mhm.
proton. Okay, and there is a football sized, I don't know if it's that they compare, I mean, if it's that the accurate comparison. If you take a football as a quark
Mhm.
inside the football field,
Mhm.
and how do they interact? Like, is there a physical touch? Like,
No.
it's like how,
No.
and do they bounce off each other?
No, they don't
Vibration?
bounce. They don't bounce of each other.
Do they
come
vibrate?
really very close to each other,
Mm-hmm.
and when they come very close to each other, a gluon is exchanged between them,
Mm-hmm.
and that produces this strong force between them.
But how come a proton keeps a boundary? Like, like there
As I
is a
told-
movement, right?
As I told you,
Mhm.
quarks cannot be pulled apart. So that is your
Right.
boundary. The limit of energy is your boundary. Beyond that energy scale,
Oh,
a new quark anti-quark pair is created.
you mean that gluon is elastic? You can extend
Yes.
To a
It's
certain
not
boundary.
The gluon produces a tube-like thing
Mhm.
which is elastic in nature.
So you
Imaginary
mean
tube.
the radius of a proton
Yes.
is where you can extend this
Quark.
quarks like
Yes.
together, like
You can stretch it apart.
stretch it apart.
Yes.
That keeps the proton's
Yes.
diameter.
Yes.
And if you stretch again, it creates another
New quark anti-quark
quark
pair.
pair. And here the replacement of the
Yes. The new quark that is created joins with this, and anti-quark that is created joins along with the quark that you have separated.
Right. In that case, can you compress a proton to reduce its radius if you are speaking in terms of
The
spherical
energy
terms?
becomes the scale becomes the energy scale again becomes so high.
We don't have the energy
No,
level
but
to compress
the
a
thing is,
proton.
energy it compress means they have compressed it to less than 0.1 femtometers. Femtometers is 10 raised to minus 15, and at this range they interact very very weakly, but as you separate them its strength becomes more and more.
It's like tension is created.
Yes.
Okay. Oh, it's elastic.
Yes.
Like
They bring it back.
if you stop
If you try to break it, but the
Yeah.
action is different.
right.
You have new
But
particles.
there is a limit. There is a threshold where you can stretch
Yes.
to. Suppose if I had to stretch the pair of this quarks,
Mhm.
it becomes elastic, right? You can stretch it
Yes.
to a point.
Mhm.
Okay, imagine that point. And now to stretch this, you need to put energy, right, to
Yes.
stretch them.
Yes. And
And
that
if you
energy
remove that energy, they will come together.
come
again.
together.
Ah, okay. Just like a rubber band.
Yes.
And you said that energy is like you wanted to tell
Yeah, that
something.
energy is enough to create a new quark anti-quark.
Oh, right.
pair.
There's like a threshold quark
Yes,
energy, something
yes,
like that.
yes.
Okay.
Yeah,
It's
this is
like-
called confinement. The quark gets confined within that particular hadron,
Hmm.
be
Which
it
is
meson,
proton. Mhm.
be it meson or a proton.
Wow. So now I want to get into
Unification.
right. Unification.
Yes.
All unification of all these
Any
fundamental
force,
four
for
forces
that. Yes.
with a single formula.
Yes. Earlier, people thought about electricity
Mhm.
and magnetism as two separate phenomena.
Right.
Like, for example, when people brought you comb your hair and bring it near paper or bring it near some light material, it
Mhm.
starts moving. What is the
Static
reason?
force.
It is static electricity.
Mhm.
So it is an electric force. So a charge, around that charge, you have electric field.
Mhm.
It is an electric force. But a moving charge acts as a current, and around that current, you will have a magnetic field, which is a magnetic force.
Mhm.
So earlier, people used to think that magnetic force and electric force,
They were separate things.
they were separate things. Hence, you have magnets on one side and electricity on the other side.
Mhm.
Later, people like Michael Faraday and James Clerk Maxwell,
Maxwell.
they found out that these form a one single force, and that was the first step towards unification of forces.
Mhm.
They clubbed electric force with the magnetic force and formed the electromagnetic force. So that was the first step towards unification of fundamental forces.
To make physics simpler.
Simpler. So they could write one single equation or one set of equations for both electricity and magnetism, not separate laws. And then came these fundamental interactions, other fundamental interactions, like
Strong nuclear force,
strong nuclear
weak
force,
nuclear
weak
force.
nuclear force, etc. So now you already have the electromagnetic force,
Mhm.
and then you have the strong nuclear force and the weak nuclear force. So weak nuclear force combined with the electromagnetic force forms the electroweak theory or the electroweak force.
Which and all combined together?
Weak
Nuclear force.
and electromagnetic force
Mhm.
forms the electroweak force, or it's known as the electroweak theory.
What does that state?
It proves many experimental observation that is observed during weak interactions. For example, you try to take a mirror image of what is happening. Now, when I'm standing in front of a mirror, my left hand looks exactly similar to my right hand. So there is a symmetry there. Whereas when certain interactions occur, you try to take a mirror image of that. They may not be symmetric.
Chirality.
Yes. For example, a beta decay occurs.
Okay.
So when a beta decay occurs, an electron comes out. So electron comes out with a particular value of spin. You take a mirror image. What do you expect? The opposite spin.
Right.
But even when a mirror image is taken, you get the same spin, which violates symmetry.
Wow. Okay. Okay.
Now, when I lift my right hand, my mirror image lifts its left hand.
hand.
The person in the mirror lifts the left hand. So, for a beta decay, the electron that comes out, if it's spin up,
Mirror image.
mirror
spin
image,
is
it
also
should be
up.
spin down. But in nature, it is always seen that electron that comes up will have spin upwards.
What do you call this phenomenon?
This is called parity violation.
Parity violation.
Taking mirror images of interactions is called parity operation.
Why
And
is it
parity is
important to
violated.
consider mirror images inside this equation? Why to make already? What is the importance of adding
all
mirror
interactions, all interactions, we need to take mirror images
images?
to check if the opposite of that will also work.
That gives a
Like-
strong validation for symmetry.
Yes. And there are other symmetries also, charge symmetry. You try to take the opposite of whatever happened. Neutron getting converted to proton by emitting a
Meson.
electron.
Sorry, yeah, electron.
An electron
Mhm.
and a neutrino. And actually, it is not a neutrino, and an anti-neutrino. What will be the opposite charge of this? An antiproton should emit an anti-neutron by emitting a positron and a neutrino
Right. In the mirror image.
in the mirror image. Similarly, there is a type of symmetry called time reversal symmetry. Well, it is not actually going backward in time.
But adding 4 dimension in the symmetry, is it?
Not 4 dimensions in the symmetry. Well, all these are worked in 4 dimensions. We are working this. We work all these things in special relativistic term.
Wow.
So time is another variable there.
Pure math here. Okay.
Yes. Now, the idea behind time reversal symmetry is the opposite of that reaction possible? You go backwards.
Just like a Tenet movie.
Yes. Reversing it.
So you mean reversing anti-neutrino electron going back in time, fusing together, giving
neutron
back the neutron?
Yes.
So what was the observation like?
In certain set of interactions, strong interactions, it might be possible, but certain set it will not be possible.
So there is asymmetry. I mean, there is no
violation of time reversal symmetry.
There are violations in nature.
Yes. So these things are perfectly explained using the unified electroweak theory.
Unifying strong, weak nuclear force to electromagnetic
Yes.
force.
Not just that, even the another unification is weak electromagnetic unified thing is unified with the strong force.
Strong force.
And that condition is what we call as the standard model of particle physics.
That is where we are right now.
Yes, we call it the grand unified theory.
Right now, we have combined strong nuclear force, weak nuclear force, and electromagnetic force together with the formal equations
Yes.
in physics.
Yes.
And they prove something.
Then they prove something. They prove that the Big Bang theory is right.
Wow.
That is, soon after the Big Bang, the energy scale in the universe matches with the energy scale predicted by the standard model. And how did they test this energy scale?
Yes.
They tested it at the Large Hadron Collider by detecting the Higgs boson. Higgs boson is one of the predictions of standard model.
Right.
And they got it there.
That's why they call God particle.
Yes. It was termed by
Right,
a science journalist, but
Mhm.
still.
Yeah. That's how it's popularly known because it proved Big Bang.
Yes.
And in the
Earliest, one of
Right,
the earliest
earliest.
phases of the universe.
Can you tell me more about
Higgs boson.
standard model and
Yes.
it proving the Big Bang? So let's get into that detail. Like it's
Yes.
more
The
exciting.
standard model combines 3 among 4 fundamental forces. So there is just one force
Who
left.
was responsible for this, and which year was it for the standard model?
It was a collective
Collective, right,
effort.
right.
It is a collective work of many people
Right.
together.
But what year was the holy grail of this unification? Like that happened and
yes,
changed
it
our
was
understanding.
somewhere in the year 1970, in 1970s,
Mhm.
by a British physicist Peter Higgs.
Mhm.
He had given a particular mechanism. Now, we talk about masses, particles. All these particles have masses. Where did the first particle come from? First particle, first mass. Where did it come from? How did energy get converted to mass? Where does this come from?
Okay.
So that mechanism, that mathematical theory was called Higgs mechanism, named after this person, Peter Higgs.
So he proved his curiosity was how
The first mass was
particle
created. Yes.
mass was created
Yes.
from
So
energy.
it is basically some symmetry broken symmetry, creating enormous amount of energy and mass being created.
But
From energy.
from
So
that
it is not
way,
just that mass is created from nothingness.
yeah, there is
energy.
Yes.
Sufficient amount of energy
Right.
for the mass to be provided.
That means before Big Bang happened, before the mass was created, that means there was
Yes.
already that much energy was existed before.
Yes.
Matter
there
neither be created nor
was
be destroyed.
enormous. At the time of Big Bang,
Energy
it was enormous.
is a collective energy of all the universe put together.
Yes.
Because we can't create or destroy energy,
Yes.
but we can
can't
convert
imagine,
that into mass.
We can't even imagine the scale of that particular energy.
Right.
Much more
Right.
than the energy of
mean,
the Large Hadron Collider.
We can't imagine from our present neural capacity.
Yes.
It is beyond our neural capacity to compute that
Yes.
the scale of the energy.
Yes.
So you mean there was huge energy
Yes.
before the Big Bang?
No. At the time.
At the time of the Big Bang,
Yes.
the symmetry broke,
Yes.
and that led to the creation of mass.
Yes.
And then the universe happened.
Yes.
Universe is collection of mass and energy, mixture of mass
Yes.
and energy.
Fluctuations in energy
Right.
will give rise to new masses.
Wow. Okay.
So that is the basic idea behind Higgs mechanism and Higgs boson. And that theory was there right from the 1970s.
But he proved experimentally.
Experimentally, it was detected in 2012, almost 50 years.
Let's say collider.
Yes, at the LHC collider. Now, many types of Higgs bosons have already been discovered
After
within
that.
12 years after that.
Wow. So where are we right now? Like what has happened from then?
Yes, so now people are probing towards beyond standard model.
What is beyond standard model?
Yes, one question is another. We have a fourth candidate for
Gravitation
fundamental forces. Gravitation. Now, what is gravitation? According to an elementary understanding, it is
Interaction
a
between
very
mass.
weak attractive force existing between masses. Now, keep two balls nearby. Do we see them getting attracted to each other? No, because the force is so weak.
And also there's influence of Earth's gravity on the...
Yeah, even then, if it was strong enough, we could have seen the balls coming together.
Right. But for that, they need mass, more mass.
Yes.
Right? Okay.
And one thing, Newton's force or Newton's gravitation is good enough. That is even being applied in satellite motion, etc.
Right. It's working.
Yes, it's working. But there are some limitations to the Newton's law of gravitation.
Like what?
Like regarding planetary motion, etc. The smallest, according to law of planetary motion, according to the mechanics that we know, the classical level, the old mechanics that we know, the motion should actually be in a plane. They should execute orbital motion in a plane. But for the nearest planets, Mercury, for example, it is not exactly a plane.
There's orientation. Or
yes, there is a slight misorientation. The orientation changes.
That disapproves
Every
Newton's
year,
law.
it's not observed every year. It's observed only every century.
Oh,
so you'll have to wait for a long time to observe it. But this was predicted by Einstein in a new theory of gravity called the general relativity.
Space-time fabric.
Yes. So according to him, gravity is not a force. It is an effect. It is an effect of space-time fabric. Effect of basic geometry. What is geometry? It is X, Y, Z, and you have different... you can form a grid out of it.
Space.
Yes. According to Einstein, each grid point has time associated to it, and he called it space-time, and he said that it's elastic.
Time
now,
is relative.
Imagine if you put a ball on a fabric, what will happen? It will sag. And what will happen is if a smaller ball approaches that sagging part? Will it directly fall into the pit, or will it slowly orbit and then finally fall into the pit? Like what happens in the case of a whirlpool. It will orbit and then finally it will fall into the pit. This is exactly what is happening in the case of solar system. So the entire concept of gravitation is just an effect of space-time curvature. So it's not just space that is bending, even time is being stretched there. So this is the present understanding of gravitation.
So gravity is also the function of time, you mean?
Yes.
Not just mass.
Yes. Not just it's not mass. It's because of the presence of mass, it's a function of space and time. Or space-time.
Right.
Now, we need to quantize it. To unify it with the other three forces, or to unify it with the standard model of particle physics, we need to quantize this gravitation.
You mean gravitation is not continuous?
It is continuous. We have to have a quantum mechanical theory for gravitation, which is very difficult because gravitation is observed only at the large scale levels, celestial objects.
Right.
galaxies, planets, stars, etc. And at the macroscopic level, it cannot be observed at all.
Smaller mass.
Smaller mass, weaker the force.
Hmm.
We cannot observe that force
Right.
at that scale. So hence,
Quantizing
quantizing gravitation is an extremely difficult task.
And how far the research have come.
New theories have come, like quantum gravity, etc., where they use principle of holography.
Like holography, 3D.
Yes. What is hologram? Hologram is a three-dimensional image put on a two-dimensional surface.
Hmm.
So here they imagine a five-dimensional actual universe put on a four-dimensional
Space-time. Hmm.
Now, it is really difficult for us to perceive above three dimensions.
Right.
So 4, 5th, and higher dimensions, it will be difficult. But there is an interesting novel, which came somewhere in the early 20th century, early 1900s. The name of the novel is Flatlands by Abbott, a British novel. Well, the idea about Flatlands is that all the characters, including the protagonist and the antagonists in the novel, are flat surfaces like circle, square, triangle, etc.
Two-dimensional.
Yes, two-dimensional figures. So the protagonist in that is a square.
Mm-hmm.
One fine day, he observes a circle changing its size. The circle is becoming bigger and smaller.
Mm-hmm.
So he asks us, is this magic?
Mm-hmm.
Then he says, no, it's just that.
Fluctuating between 2-dimension and 3-dimension?
No, it's just that we are not two-dimensional structures. We are three-dimensional structures. The thing is, I'm moving up and down.
Mm-hmm.
So when you view a sphere moving up and down, what will happen? The circle trace will become bigger and smaller. But when a square does the same thing, what will happen? When a cube does the same thing, what will happen? You will trace only a square which never changes its size.
Right.
So the square doesn't know that he is actually a three-dimensional cube. And in the novel, what happens is, he understands this phenomena. He starts preaching it to all the other
Cubes.
Cubes, triangles, etc.
Mm-hmm.
Finally, he is executed for that. Same thing which happened to Copernicus and Galileo.
Right, right.
So, the takeaway message from that novel is that for a two-dimensional world, it was very hard to visualize a three-dimensional
reality.
So, for us who can easily visualize a three-dimensional world, a four-dimensional reality is difficult, but we can use it or we can understand it with a certain set of equations.
Mm-hmm. So what math is needed to...
the kind of math they use is now, apart from quantum gravity, where
Mm-hmm.
holography is used, there are other theories like string theories,
Mm-hmm.
where the number of dimensions are multiplied. They go to 8, 16,
Mm-hmm.
more.
Mathematically, there's 26
Yes.
dimensions possible.
Yes.
So all dimensions are combined in string
Yes.
theory.
So basically, they try to combine all these forces,
Mm-hmm.
all these theories using symmetries. So they call it supersymmetry theories, strings, superstring theories. There are many theories which work in this area.
So these are the efforts to unify gravitational force with the standard model.
Standard model, which
Mm-hmm.
is a unified
Right.
force.
You said one is quantum gravity,
Yes.
where you try to quantize gravitational force.
Yes.
It's very difficult. That's why holography comes in.
Yes.
Like you try to visualize from higher dimension.
Yes.
So second thing is string theory.
Yes. Strings, where you consider every particle to be a string, a closed string. So all its variations, energy variations, is
Like
given
vibration.
by a particular vibrational state of that string.
So you mean we all have different vibration?
Yes.
The reason why you
Not
are
just
unique.
me.
Yeah,
yes.
everybody.
Not
All
just
the
me.
matter.
All the matter.
Right.
All the particles that are there. So that is why I am unique and you yourself are unique.
Because my phone is vibrating differently, that's why it's phone.
Yes.
This chalk is vibrating differently,
That's why it's a chalk. And it's white in color.
So there is a conflict between string theory and quantum gravity.
Conflicts between
Are there any
almost
other
all
theories?
Super string theory, supersymmetries. Now we are working in symmetries. Supersymmetries are higher dimensional symmetries. And then there are one important theory, the dark matter and dark energy theory.
Oh, that is a holy grail of physics, right?
Yes.
Like nobody can even imagine what dark matter is.
We can imagine. That is, now there is certain amount of light in that area. Now it is already proved that dark matter exists, but nobody has detected an actual dark matter.
Okay, let's focus our conversation back to, on dark matter and dark energy.
Yes.
So, yeah, what are the dark matter and dark energy?
Let me explain it. Try to explain it in a simple manner. Now, imagine you measure the entire energy of the universe by some observation, or not observation, by some mathematical model. So you have a total energy, and based on the acceleration that is happening of all the celestial objects,
expansion of the universe,
yes, based on that you have an observed value of energy. So the calculated energy or the predicted energy does not match with the
expansion energy,
which means that there is some underlying mass
which is responsible for universal expansion.
Yes. And some underlying energy
to drive the expansion.
Yes. Acceleration. According to the theory, according to whatever theory we have, universe is expanding. After some time, it should decelerate because there are masses. The masses should start attracting each other. So universe should fall in.
That means again,
after it expands for some time, it should contract. But that is not observed at all. Only an acceleration is observed. Even after 14 billion years of its creation. So there is some invisible energy and there are some invisible matters responsible for all these things. They are dark matter and dark energy. Well, there are some observational evidences.
But nobody could visualize it.
Nobody could actually see or detect an particle like
dark matter.
For example, now consider one of the predictions of general relativity is light bends around any heavy object. Heavy
black
object
hole.
In the sense around black hole or around a galaxy or even around sun, light will bend. That is, a galaxy lies beyond our sun. So the light from that distant galaxy bends when it moves very near to the sun. So it bends and comes towards us. So there is a bending of light because of the space-time curvature. Because light traces the path of the curvature. Now, in certain cases, bending of light was observed even without presence of any object like the sun.
That's where dark matter was.
So there is some matter which is responsible, which has mass, which they called as the dark matter.
But do you think it would have an atom? It would
we
have
don't
other
know.
properties of matter.
We don't know.
Yeah, it is still a black box.
We don't know. But there are theories, like there are baryonic dark matter, non-baryonic dark matter. There are many theories.
But ultimately it should have some fundamental particles.
So if dark matter, so they are trying to address dark matter using supersymmetry theories. So if by any chance a dark matter or a set of dark matters are detected, so one among these beyond standard model theories will become a grand success, and that will result in unification of the fourth force with the standard model. So I
Nice.
think we can write a single equation for the entire universe.
That will be like a singularity. In a sense, you can explain any phenomena in one
Yes.
theory, one formula.
Yes.
From the subatomic level to the cosmological
Yes.
level, you can explain the physics
Yes.
in one formula.
Yes.
That is
It
what
should be possible.
the unification of standard model
Yes.
and gravitation would lead to.
Yes. But for that, experimentally, the scale again, we are at tera electron volt scale. We may have
That is for the experimental level, but for the theoretical level, I think we need to I think
no,
we
theoretical
more
level already predictions are there using super symmetry theories.
symmetry.
There are
Yes.
predictions of many types of dark
Oh,
matter.
Right. Okay, right now we have three major candidates: quantum gravity, string theory, and supersymmetries. Now all these three candidates
Predicting.
are waiting for the energy level where we can get inside these quarks or the dark matter
and
to
detect them.
And that would
Result-
prove which of the three would be right, or they are all wrong.
Yes.
Oh, finger crossed. Do you think we would arrive in our lifetime unifying?
Well, Peter Higgs waited for 50 years for
Right.
Higgs boson to be detected.
Right.
And Einstein's gravitational wave theory,
Mm-hmm.
something which was predicted in 1915, it had to wait for 100 years. It was first gravitational wave was detected only in 2015.
Right.
So
Right.
it may happen.
Do you think is there any chance that Einstein would be wrong, just like the Newton would be wrong? Like Newton is wrong in some
Newton was not wrong.
But
there was some
not wrong.
Newton's force is right up to a certain limit.
Right. Classical mechanics is all on Newtonian.
Yes.
This thing.
Yes.
Just like that, after Einstein came up, then the new field came up, relativity.
Yes.
Like the quantum. It was there.
We may get a new theory
Mm-hmm.
of which a lower limit will give you the Einstein's theory.
Right.
Lower limit of Einstein's theory will give you the Newton's theory.
Right.
So lots to be done.
Wow. Times are exciting. Future.
Yes.
Like, what are the questions you are personally excited for? Like, you wait up, you are really curious about in terms of this physics.
One is various mechanisms that happen
Mm-hmm.
that are unanswered even now in the field of particle physics.
Like,
for example, lots of things to be answered in quantum chromodynamics regarding exact form of potential.
mm-hmm.
See, we have given our theory need not be right or it need not be perfect.
Mm-hmm.
It matched with the experimental data. But tomorrow, who knows? Maybe a better theory might come, with a better potential. Well, I'm sure might have already come.
Mm-hmm. So, what are the other questions in quantum chromodynamics?
Other questions in quantum chromodynamics. One is obviously a better or a perfect form of a potential or form of perfect equation for the force.
Mm-hmm.
And there are other like regarding symmetry breaking, etc.
Mm-hmm.
There are lots of ambiguities.
Mm-hmm.
Why all these symmetries are violated? For example,
that is not at all answered yet.
Some are answered, some are not answered.
Mm-hmm. So that means we need new math. In a sense, there has to be a new field in mathematics for us to visualize symmetry.
We have the mathematics, we may have to go deeper into it.
Help me visualize.
For example, when group theory was formed in mathematics,
mm-hmm.
they never knew that its main application would be here in particle physics.
Right. Right. Oh, they
So
have to connect the other fields.
deeper.
Right,
We may
right.
have to go deeper.
Okay, I think that needs more imagination.
Yes.
Knowledge is already there.
Yes. Imagination and trying to connect.
Right, that's what imagination. You're
Yes.
trying to apply the knowledge already existing to other fields or the.
Exactly.
So for the budding physics students out there, like
Mhm.
who are really into particle physics, high energy particle physics, or who
Or cosmology.
cosmology,
Yes.
or even subatomic level.
Mhm.
What are the exciting areas? Like we already discussed, exciting areas
Well,
like dark matter,
the-
dark energy.
The best areas are solar physics.
Mm-hmm.
Sun has many unanswered questions.
Mm-hmm. Like what are the
Experimental
top
ones.
3 questions in
Sunspots.
terms of science?
Sunspots.
Why do they appear?
Why do they appear? What happens to the sunspots?
Mm-hmm.
All these things. There are answers because of magnetic field variations,
Mm-hmm.
but still, we have not gone there and we have not
Right.
observed it.
Right.
So that is why we have this Aditya L1 mission.
Mm-hmm. Observing that can give us more understanding on
Yes.
nuclear fusion.
So Aditya L1 is recruiting more and more researchers into it.
Brilliant.
So like this, there are many unanswered questions just in our solar system,
Our own sun.
and our own other fellow planets,
Mm-hmm.
and then go beyond the solar system. You have
Right.
many such unanswered questions. So at a large scale level, you have these,
Mm-hmm.
and smaller scale level, you have many unanswered questions in all these theories. And also, all these quantum mechanical theories are being applied into latest technologies in by spintronics and quantum computation. So
Yeah,
there-
this knowledge has to be translated to its fullest
Yes.
application.
yes,
That brings me another question. Just like studying, atomic physics or nuclear physics
Mhm.
gave rise to atomic bomb,
Mhm.
or nuclear reactors. Like
Yes.
people could imagine so many possibilities
Mhm.
on its application level. But if we get into subatomic level,
Mhm.
which is when we deals with quarks, these gluons, I don't know. I'm not aware about the applications.
Yeah, it is
Like,
being used.
right, what are the
It is being
applications?
Best,
Right
well,
now.
the latest technology of LED smartphones, LED smart screens, etc.
Mhm.
They are made by smaller scale accelerator setups. You have a very low energy accelerator to fabricate these things.
Help me visualize it. Like you mean each screen, like each cell in
E-
the screen has
each-
its own accelerator.
Not cell. This is actually an LED, which is a solid state device.
Can
So
you
to
repeat?
fabricate
Mhm.
this LED
Mhm.
is a solid state device.
Mhm.
So to fabricate this, you have to create layers of materials. And these layers of materials can be deposited only using accelerators. Well, we have one in India, RRCAT, Raja Ramanna Center for Atomic.
Mhm. So any other application apart from
Usage of that is, see, it is after a bombarding.
Mhm.
After bombarding, you will get many residual particles. These residual particles are used for such technological applications. So in every collider setup, research collider setup, there will be a technological wing which will be
Oh.
waiting for where we can apply it.
Wow, you mean the TV, the mobile screen, or whatever
Yes.
as the visual equipment, I mean the
Yes,
visual
yes.
element is nothing but a collider.
Not a collider, a byproduct of a collider.
Okay.
It is created using a collider.
Okay, and I've also heard scientists hypothesizing
Mhm.
that in the future people may roam around with the pocket particle colliders. Like right now, the particle colliders are the
Well,
like,
now if you
range-wise.
can have colliders in hospitals
Mhm.
to treat cancer,
Wow. Okay, this is very possible. I feel.
Mangalore has at least 4 of them.
Okay, connect them all of
AJ.
it with one collider and
No. They have small individual colliders in their hospital.
Magnetic nuclear resonance, MRI.
Linear accelerators. They accelerate radioactive particles, and they are fed into that is they are used for cancer treatment
Even diagnosis.
and diagnosis. One is creating a very high energy situation like that of the sun for fusion research.
Right.
That is another application that it can have.
Studying subatomic interaction would give us better knowledge to have a viable nuclear fusion reactors in the future.
Yes.
So there's a lot of questions to be asked.
Yes.
There is
So
a lot
controlled
of new knowledge has to be discovered.
Yeah, controlled nuclear fusion means that should solve almost the entire energy crisis.
Right. No, and even in general terms in physics.
Yes. Lots to be answered, lots to be asked.
Yeah, right questions to be asked.
Yes.
Right knowledge to be discovered.
Right.
And also find the use for the existing knowledge.
Yes.
And future
finally
self, right.
apply everything for common use also.
Right. I think now I understand we need more physics graduates.
Yes.
And bright minds working in physics rather than in other industries. I think you would have a lot of things going on your head. Particles.
Yes.
So do you think about the problem solutions, equations when you're doing your daily chores at home?
Not just that. The best thing is we get a lot of time to do research as a part of our job here, of our work here, along with academics, teaching, and other works. A lot of time is given to do research, and a lot of help is given by the management here. And really have to thank the management, vice chancellor especially for the kind of motivation that he gives for research. Because he is really into this research and all this stuff.
Like how do you are a academic, like you teach students. So how time consuming is this whole research on particle physics?
Well, whatever.
Like how do you manage?
Well, since particle physics, since my area is theoretical physics, I don't need an experimental setup as such. So I can also sit and work.
Just time is needed.
Yes, time, patience is needed. So whatever time that I'm not utilizing for my teaching or my other stuff in the institute, I can dedicate it for my research work.
Do the institution know what you're working on?
Yes, knows. My area is theoretical physics. The management really provides support for this kind of research that we are doing in our area. And the kind of support that vice chancellor and other even other my senior faculty are giving me, it is extremely helpful.
Okay, support you mean not just giving you the time to sit and work on this problem, but also making you government funds available to this research?
Not just government funds available. Our management, the MJES, provides funds for research.
Okay.
So I currently am working on an MJES funded project.
What is MJES?
Mangalore Jesuit Educational Society.
Okay. Oh, nice. They are the funding.
They fund for your project.
I just had a podcast.
I can procure my own instruments for that. I can procure my own software for that.
Okay.
For this, because for my work, after I derive all these things, I need to simulate them using some coding.
Right.
So to procure things like Mathematica or MATLAB, I need money. So I get it from funded projects. So I work on a funded projects from the MJES. So I really thank them for the kind of support that I'm getting. Well, softwares like Mathematica comes in lakhs for that.
Oh, is it?
Yes. Okay. So to procure them.
And what about the hardware on that? Like it can run on any.
Mathematica can run on any modern computer. So that you don't need a very big computing station for that.
So suppose if you had unlimited resources, like you got huge funding,
Mm-hmm.
let's say, and you have a good capability. You have a
Mhm.
solid team
Mm-hmm.
of your own, like
Yes.
small physicists or intern physicists, you could say,
Okay.
okay, who have solid understanding on math, on each areas,
Mm-hmm.
and you are a perfect team now. So, what is that thing in particle physics that you would put your full focus?
We will first try to fix all the problems in fundamental areas like quantum chromodynamics and
Mhm.
weak interactions, and
So,
then go towards the final part, which is unification.
okay, is anyone in India is working on that regard?
In practically in every institute, there is one or the other working in
Mhm.
many of these problems.
Yeah, it was a pleasure to talking to you, sir. Like
Thank you.
you answered a lot of my. I mean, you give me a new symmetry in my mind to think about.
Well,
Like you give me another dimension to
uh,
think about.
the entire dynamics of nature is
Nature,
symmetry.
right?
So
I feel like we're
you
in
have
all
to.
illusion in a different screen. I mean, I feel. I mean,
Yes.
like could be a possibility now.
Yes. Yes.
All right. Thank you so
Oh,
much.
thank you.
Yes.
Thank you very much.